In the final topic of this unit, I would like to present an argument typically known as the water filling argument, which is used for power control in communication systems. So power control is employed in various scenarios. The scenario we have in mind is when you don't have one channel but several parallel channels, and the resulting power constraint, the power constraint that we were applying on code words earlier, must be applied to the code word transmitted across these parallel channels. So, for example, you can consider the OFDMA, which is in LTE. OFDM is a uh, multiple access scenario where you use different parallel channels to give access to different users. So you can think of downlink communication in LTE, or even in the new Wi-Fi standard called Wi-Fi 6, OFDMA is now available. So you can think of OFDMA where there is parallel channels, and then the question becomes, how would you distribute power across these parallel channels to maximize the capacity? Of course, this is just in some sense, a theoretical question because the actual standard is quite complicated, and it is not immediate to see how the power control part directly enters the capacity calculation because of how the standard structures the positioning of code and then the modulation scheme. But nonetheless, the calculation that we'll do in this lecture will give you an idea of what nuances lie in this power control. So suppose, coming back to a nice clean theory world, suppose that instead of 1 we have say capital K parallel additive Gaussian noise channels, okay, with noise variances, different noise variances, sigma 1 square, sigma 2 square, and sigma k square. Okay, suppose you have that, and now we want to satisfy the power constraints across the channel. So you will send, so in each transmission you will send one code word for each channel. So let x k1 to xkn be the, just write it cleanly here, this is what you send, xk1 to xkn is the code word sent over n users of channel k, and k is in one of these capital K channels. Okay, so we assume for simplicity that all channels are used exactly n times, all of them. Okay, and now we must satisfy the overall power constraint across all code words of all channels. Overall average power constraint of P. So what does it mean? It means if you look at total power sent across all the channels across time, that must be at most NP. That's the average power constraint. This average here is over time. So that's the average power constraint. Okay. Equivalently, for each K, it's not really equivalent because we need not have pk, we need not have finite pk, but let's assume that for each k we assign the power pk, average power pk, and what we want is that summation over k equal to 1 to k, pk is less than equal to p. So this is not equivalent because for each k we need not have power growing with n, okay, but still we are requiring that. So this is the power constraint that we will impose, okay, and it can be shown. I will not show this because the proof is not so difficult. You can do it as an exercise. That the capacity of the parallel channels or the of the parallel channel, so the combined parallel channel, is given by summation k equal to 1 to k half log 1 plus pk by sigma k square, k powers. This is the SNR for that k channel. But now you have this pk's in your hand, so you maximize over all p1 to pk such that summation over k pk is less than equal to p. Okay, this is one condition, and second condition is all pk's are greater than equal to 0. Okay, so this is now the capacity of the parallel channel. Okay, and what we figure out is how do we distribute the power across the channels. They all have different noises, but how do we distribute it? When one heuristic is that a channel with more noise should be given more power because uh, well because there's more noise, so you need more power to compensate. But on the other hand, if you give more power to a channel with more noise, this channel anyway is less rewarding. So why should we give it more power? We should give it less power. We should try to focus our power on the channels with less noise. So which of these two sort of contradicting heuristics dominate? So let's not just forget about the heuristics and just do the maths. So we'll optimize this guy. So what we want to look at is so this is the typical Lagrange multiplier approach. Okay. Uh, what we will do is instead of solving this optimization problem, we'll bring in a Lagrange multiplier here. I'm sort of also teaching you how this Lagrange multiplier thing works. So note that for every lambda 0, for every lambda greater than equal to 0 of your choice, the maximum above this maximum, the capacity here, is less than is less than this max here is less than, so this part I retain, but I add to it some lambda times some non-negative quantity. What is the non-negative quantity I add? It's p minus summation k equal to 1 to k pk. Okay, that's the part I need. But I still need a max over all pk such that they are non-negative. So what I've done is I've taken one constraint and put it here, and for any lambda this is less than equal to this. So we will try to first maximize this guy here, okay. So we'll call this f lambda for a given lambda p1 to pk. How do we maximize this? We'll just differentiate this by pk. What's the partial derivative of this with respect to pk? Yeah, so that partial derivative is half into 1 plus sigma k square by pk square minus lambda. And this is true for all k between 1 and k. Therefore, this f lambda function, this one here, it is increasing in pk. So this is some things we are noting. Increasing in pk till pk equals to 1 by 2 lambda minus sigma k square, and decreasing after that. Okay, so if this guy here is negative, the function is decreasing for all pk greater than or equal to 0. Okay, and therefore you should put pk equal to 0 if this guy is negative. But if this guy is positive, then then the optimal choice of pk would be this itself. Thus, f lambda p1 to pk, even if we ignore this constraint, is maximized for what? For pk equals to 1 by 2 lambda minus sigma k square, the positive part. So what is this? So this is some notation. X, the positive part of a number x is max of x comma 0. So if it's negative, you just put 0. Okay, that's what it is. And that's what we discovered here, that if it's negative, you better put 0 because it's decreasing throughout. Okay, so this is the choice that you must have for all. Okay, and we have ignored this constraint, but anyway the solution has this, satisfies this constraint. So we don't worry about this, and this maximizes this right side, but not the function that we actually wanted to maximize, but it maximizes the right side. Okay. But we can choose any lambda we want, and still it will be a maximizer of this side, and it will exceed whatever you can do here. So what if we can find a lambda for which the power constraint is satisfied? Then this guy would be less than this because it's true for all lambda, but then whatever lambda we have, we'll get an expression which is less than this. Okay, so in particular, the max in this equation here, the capacity expression hash in hash is equal to the max of f lambda p1 to pk for lambda such that the power becomes equal to summation k equal to 1 to capital K 1 by 2 lambda minus sigma k square. Okay, so if you make this equal to this, then power constraint is satisfied, and but for this lambda, whatever answer you get here exceeds this side anyway. So this tells you this is the right power allocation pk. This is the optimal power allocation pk. So can you find such a lambda? And the answer is yes. For lambda equal to 0, this quantity is infinite, the right side. And for lambda equal to infinity, this quantity is 0. And as lambda increases, this quantity decreases. So this comes from infinity to 0. At some point, it must equal this p. Okay, so we can always find such a lambda. In fact, we can easily depict this lambda in a figure, and that explains the name why optimal power allocation is called is given by a water filling argument. This is how we can see this optimal lambda. We think of this sigma 1 square. We think of this sigma 1 sigma 2 square as some blocks like this of different heights. So this is like the surface of your rocks, and drop it more carefully. So this is your bucket, and you want to fill water in this bucket. Okay, how much water do you want to fill? You want to fill water, overall water volume, that is P. Overall volume P. And so what you do is this level that you have here, you go to a fixed level, this level here. This level is for you 1 by 2 lambda, this thing here. So what is this guy here? This is 1 by 2 lambda minus sigma k square. Okay, so this is pk. Okay. And similarly, this would be p1. But what about some of the places where the surface is more than 2 lambda? Well, no water will be filled there, and that's why you have this plus positive part. So this is exactly equal to, this distribution is exactly obtained in this manner. You think of a bucket with this different surface, and you pour water of volume P on it, and the level that you get above each part is exactly the power allocation for that part. Okay, so this is the power allocation for the first part, this is the power allocation for second part, third part, kth part. Okay, these are the power allocations. So that's why this optimal power allocation is given by a water filling argument, and it comes out of an optimization problem. So note that what is the answer to our question? Where do you assign more power to something with more noise or less? Well, you assign more power to buckets with less noise. Okay. So here the power is more, less, and then more. That's for sure. But there is a non-linearity obtained because of this plus part here. Okay. Below 0, you don't. Below a certain level, you don't assign. If the noise is greater than something, you don't assign any power at all. And that's the optimal solution. Okay. So in particular, when you substitute this, the capacity is given by half over k, such that, take this b, this one might only sum over those k's for which b exceeds, b is this 1 by 2 lambda, exceeds sigma k square, the noise, and then this is the difference is the power, so it's b minus sigma k square plus sigma k square by sigma k square, so that's just this, right? And what kind of b do you choose? You choose a b such that when you sum all the power given to these guys, then that's exactly equal to b. Okay, this is the capacity. So you solve this to find b. This is the solution here, and then you assign it this way. Okay, so that concludes the final lecture of this part, and in fact this concludes the NPTEL course. We have covered in this last two units. We have covered channel coding. We defined the channel capacity problem. In fact, in the last I think it's the last three units we have covered channel coding. We defined channel capacity problem, showed proved proved Shannon's channel coding theorem for discrete memoryless channels, and in this final unit we showed Shannon's channel coding theorem for the Gaussian channel, for the additive Gaussian noise channel in under power constraints. Um, this was presented as a theory, but this theory has led to design of practical codes which can attain this capacity. And further, it has those codes are mirrored to communication system where the channels are not exactly of this form, in some sense much more complicated. But still, these ideas have been used quite a bit in communication systems, in the design of error correcting code for communication systems, and in many other places for power control, and many at many places. Okay. Before channel coding, we saw compression. We saw compression for problems where the source model was known. Uh, Compression for the non-model case, codes such as Huffman codes, why they are optimal, which are variable length codes. We saw why they are optimal. Other optimal average length codes, and we also saw universal compression in that part. And before that, we were just covering some fundamentals of the course. At least half of the course was targeting discussion on fundamentals such as the definition of entropy, mutual information, divergence, and the origin of those definitions. We gave problems which led to these definitions naturally. So this is the end of the NPTEL course. I hope you enjoyed the course.